Welcome to another interview for the Zero to ASIC YouTube channel. And today I'm very happy to be joined by Dirk and Nguyen, who are both involved in the fabulous FPGA fabric. They were involved in the MPW2 tapeouts with eFabless recently. And today we're going to be talking to them about their project and their experience on MPW2. So welcome, Dirk and Nguyen. Nice to see you both.
Thanks for the kind invitation.
And you're based in Manchester, Dirk?
Yes.
And Nguyen?
So in the background, what you see, that's Manchester, a little bit of it.
Nice. The home of the Industrial Revolution.
Exactly.
Nguyen, whereabouts are you based? Are you also in Manchester?
Yes, I'm in Manchester.
Not quite so high up.
In the room. For the postdoc, it's not a lecturer.
And can you tell us a little bit about the fabulous FPGA framework?
So this whole project started with the Forte project, which is a 6.3 million UK platform grant. Yeah, so it's quite a substantial amount of money with Southampton at Imperial College. And it's researching memristor technology for building reconfigurable devices. And we here in Manchester look actually into building FPGA fabrics using memristor technology. And in order to do that research, of course, we want to build chips at the end of the day. I started very early on building this framework in order to have full control over the whole flow, including the ASIC generation, but also using open source tools, integrate them in order to have CAD tools so that you can take, for example, your Verilog and run it on your chip. Yeah, so that was kind of the origins. Yeah, and then I had a little bit of a sabbatical. And I had like a couple of weeks, months time to program that. And then I was joined by a larger team. And we have now quite an active community moving this tool forward.
So how many people are there in the team then?
Oh, at the moment we have, well, it's myself, it's Win, it's who's doing the ASIC part and the physical backends. We have Win working on the FPGA CAD tool integration, and we have two summer project students working for a couple of months now and adding some optimizations and polishing the tools.
Okay, and you said you'd taken a sabbatical. How long has the whole project been running for?
Forte itself is now on for 2 years roundabout, and I would say pretty early on we started with Fabulous, yeah. But it took a little bit time before we went live with this because we wanted to have a certain quality that it's really usable, that it works reliable. Yeah, and we had our first tape out now that came back and the chip is working, so we know it does the job.
And so that was before the Google eFabless announcement, I take it.
Yes, that was a TMSC 180 nanometer process. It was just because this was like an MPW that we did within the Forte project with the just along the project partners. Yeah, and we went for an old process because of cost reasons. Yeah, and as part of that tape out, we did our first chip, which was a small FPGA fabric coupled for custom instruction set extensions with a RISC-V CPU.
That sounds really interesting. We'll get a bit more into that later on, I think. So I don't know if you've seen. I don't think you were involved in MPW1, were you? Just
No.
MPW2. Okay. So I've seen quite a lot of FPGA fabrics on MPW1 and 2, maybe like 4 or 5 different ones. Have you checked them out?
Well, there is basically the other ones, or in the first one, that was the Open FPGA initiative. Fundamentally, we have kind of similar goals, use similar approaches, probably are pretty similar in terms of quality of results. The open source FPGA CAD tools are very similar. There are, however, a few things where we differentiate, where we think they are important, in the sense that the OpenFPGA project comes from the very established VPR framework, which is a long-standing open source tool to do design space explorations for FPGAs, which is something you want to do if you want to build an FPGA from scratch. And we basically wanted to have a different approach where we say, if you know already what your FPGA fabric should look like, you may not necessarily need so much design space exploration, point one. Point two, using design space exploration is a very tricky beast. And it comes with a lot of complexity that you usually don't want to deal with if you want to build a complex SoC and just embed your FPGA. And the philosophy is in Fabulous that we provide you a view that is a little bit more what you know from Xilinx, where you say, oh, I have a CLB column, I have a blockram column, I have a DSP column, and you can compose them together. Nevertheless, you can still parameterize everything, and you can say, I want lookup tables that have a certain size. You can parameterize the switching fabric, those kinds of things, But it's a little bit a different philosophy that we come basically that we say, okay, we provide you, for example, a Spartan 3 clone, and you can adapt it to your needs. For example, kicking out some wires, playing around with a number of columns of logic and so forth, And there are also on the technology side one fundamental difference, and that is that the OpenFPGA fabrics, they use shift registers for configuration, which we find quite problematic. This would dive a little bit too much into details probably, but if you think of a normal CLB tile, that's like a logic block that bundles together a switch matrix and a couple of lookup tables. You need round about 500 to 1,000 configuration bits. And the way we do this in Fabulous is that we organize these configuration bits like in words, typically in our case 32 bits, but it could be anything else. And we write basically word-wise, almost like what you would do in a memory array. And you can selectively update individual bits, what you need for partial configuration. What OpenFPGA does, they daisy chain all these configuration bits together and form a very long shift register, which means in a large FPGA fabric, they have eventually thousands of configuration bits that they have to shift in, which causes huge dynamic power, which you don't want. You may configure during configuration ring oscillators, all kinds of transience effects that you typically don't want. And you can't really do things like partial reconfiguration, which was a thing that I definitely wanted to support. Also, there is an advantage with doing this is that for configuration storage itself, I just need latches. I don't need flip-flops. In order to offset the cost for flip-flops, OpenFPGA does custom shift registers or custom flip-flops for configuration storage. We don't have to do this. We can just take a standard cell latch out of the standard cell library, and we get basically the same area. Other things like how to implement switch matrix multiplexers using, for example, custom multiplexers, that's supported in both frameworks.
Okay. So one of my future questions that I think you just answered was about the configuration. I was interested, so really the only FPGA fabric that I'm used to is the ICE40. And I know that's a 4-input LUT with a flip-flop and some carry logic. So you're saying that with the Fabulous FPGA architecture, you can kind of have a configuration that says, okay, I want a 6-input LUT, or make those kinds of decisions?
The way how we do that is I kept Fabulous deliberately simple, but generic at the same time. For our first tape out, and we actually took a lot of these concepts also in the shuttle run, in the second shuttle run in that fabric, is essentially we went for the ICE40 logic cells, and I just did it because all the Yosys NextPNR, but also VPR work is very well supported for that device. So I don't want it to take a high risk. I can model any FPGA architecture. I can even model ultra scale devices from Xilinx. I can model Altera devices, and but I went deliberately for the ICE40 just because they are so well supported in the open source CAD tools, and I wanted to have something that's reliably working. We added a few kind of own features, like DSP blocks with a wider accumulator and so forth, which you can also then instantiate. And then this was just the logic tile. But for the routing, I used essentially a Spartan 3 routing graph. I work on low-level FPGA aspects for a very long time, and I know in detail the architecture graph of Spartan 3 FPGAs. And well, Spartan 3 FPGAs, they are now 20 years old, so all patents are expired, so we could consider them as kind of usable for us all, right? And so I used basically that routing fabric, and I took this architecture graph and just put it into our Fabulous model, which is relatively easy to do, and combined this into a fabric.
So maybe that's a good point to move on into talking about the support with the open source CAD tools, because one thing that I was quite interested to see was that out of the box, NextPNR and Yosys will work for the designs that you've put in MPW2. Yes. And I've seen a few other projects and spoken to a few other people, and it seems like that side of things is a bit less well developed. So it's really interesting for me that, say, if you were kind enough to send me a sample from your MPW2, I would be able to use Yosys and NextPNR to put a bitstream on that FPGA with the open source tools.
Yes, this is we have quite some work growing on in the background, making this all happening. So they're actually at the moment, it's one student working full time for a couple of weeks, months, polishing the VPR flow, getting this run. So we don't want to limit anybody, and we basically generate VPR models out of Fabulous. And we, at the same time, we have Ying implementing the NextPNR path, the Yosys NextPNR path, and that are really people working full time now for a couple of weeks doing this. So it's not trivial, but it's doable. And it's actually not so super hard, because fundamentally we have the architecture graph modeled in our Fabulous tool, and we use it to generate the ASICs. And if you want, so you have to write a different backend to generate the architecture graphs in a format that the CAD tools understand. And of course, there is a little bit more to do, that you get also the timing information out of the ASIC later and annotated into the FPGA CAD tools, because they can all do timing-driven place and route.
Actually, that's a really interesting point, just to interrupt there, was I know that one of the shortcomings in the open source tools as applies to the reverse engineered FPGAs is that we don't have the precise timing information. So NextPNR is always a bit conservative to make sure that your design works. and that last bit of performance isn't accessible because we don't have the full timing information. But I suppose that's something that's really great about doing an open source FPGA, because we will have the exact timing information. We can get the best performance out of it.
We are doing even more. There is work by Dia. It's actually another PhD student working on this one. He started originally working on our FPGA virus scanner work, and we try to build like a scanner that detects aging effects, which is fundamentally the same thing that you need if you build your own FPGA and you want to characterize that one. Yeah, and he's generating test configurations to validate or to precisely characterize the timing information from the ASIC, so we can actually see how what the real chip looks like and what the ASIC cut tools will report us. Yeah, so we get even an extra level of confidence. There's something more we add. We don't think it's absolutely needed or necessary, but we are actually building a validation tool that ensures that the open source CAD tools and the silicon are all based exactly on the same model. Yeah, we have, of course, like a correctness by construction approach, that we go from one golden model and derive the silicon as well as the models for the CAD tools. But we talk about quite a complex software stack, yeah, and like you do some levels of checks if in the ASIC world, if transformations are correct. We want to ensure we are building tests actually that ensure that the silicon and the FPGA CAD tools are based on the same model, to just give extra confidence.
Okay, and one further question about Yosys and NextPNR before we move on. How automated is that process? Let's say I want to embed some FPGA fabric on my next tape out, and I say, okay, I want 200 lookup tables with 4 inputs and XYZ. How much work do I need to do to be able to synthesize a bit stream, and how much is automated?
It depends what you do. If you one way is in our case, that's a little bit different in VP in how you model the primitives like CLBs and multiplexes and maybe cascading or lookup tables, cascading multiplexes, carry chains, and so forth. There are some differences how VPR does it and how the Yosys NextPNR works. Yosys NextPNR or the NextPNR path is more abstract in a way that they don't look too much into the internal details of those tiles, which has pros and cons. So it's not very well suited to do design space exploration. For example, that you say, oh, should I be able to combine 2 lookup tables together? Or should I have a fractional lookup table? And if I have a fractional lookup table, should I have separate latches or flip-flops at the output, and so forth? So if you want to explore those kinds of design decisions automated, that's something for VPR. In NextPNR, if you want to do these things, you would have to put this into our model a little bit with manual work. However, if you say, I have like a standard cell library, like that you say, or standard block library of CLBs, of DSP blocks, and they are once designed for our flow, then you can stitch different fabric sizes together. You can even manipulate with the manipulate the routing fabric, and everything is automatically generated, and you can just program in Verilog, and you don't touch the internals of the generated files anyhow manually.
So it should be fairly straightforward then, if I wanted to do something with a standard architecture. That's really great news.
That's the plan. Yeah, so the idea is you can still add your own custom blocks. That is also per se relatively easy. If you want to do, for example, our DSP block, where we added like a wide accumulator to show that we can handle tiles of multiples that are bigger than, for example, just a simple logic tile like a CLB. To demonstrate such things, it is that in Yosys NextPNR, if you use in Verilog later the multiply operator, it can automatically infer directly from Verilog the multiplier. But if you want to infer the accumulator, you have to instantiate it as a primitive, which is pretty much the same thing what you would do in a Xilinx FPGA as well. Yeah, and however, that you can do this, that the multiplier is automatically inferred, that needs some handcrafting, if you want so, to get it into the model. It's not difficult to do, yeah, but if you have once such a tile, you can reuse it over and over again.
Okay, great. So maybe let's move over now to talk a bit about the applications that were made on MPW2. And Win, maybe you could tell us about, I think there were 2 applications that used the Fabulous framework. Is that correct?
Yes, that's correct. So the first one we implemented big fabric, which is purely the COB, the DSP blocks, and also the BRAM blocks. And the second application, so we integrate with the RISC-V core. So we have 2 RISC-V core, and we have the embedded FPGA in the middle.
Okay, so the first one was like more just of a kind of test that everything is working.
That's right, kind of, yes. Actually, we got the first step out with TSMC, and now we try with the Skywater 130. And yes.
Okay. And I looked at the die for the second one with the 2 RISC-V cores. That looks pretty interesting. Could you tell us a bit about that?
Well, but basically, the actually I in charge for the eFPGA, and that score actually come from Andrew, so one of the previous postdoc in Manchester, and actually he implement everything the RISC-V core with the SRAM all from the OpenLANE flow with OpenLANE flow, and so we integrated together. So I took his CPU core with the SRAM and it integrate with the OpenLANE flow, and so we come out with the whole fabric and with the CPU.
And how many logic tiles were there in that second application, out of interest?
We have like 6 by 10, 6 column by 10 rows, yes. Because of we have to fit to the to the caravel, so we need to. So it just depends. So we have the fixed the core area, and then it just depends how much area left, and then we fill with the fabric.
Okay. And for the logic tiles, are they using all just standard cells from the Skywater PDK, or did you have to make anything custom?
Yeah, I did make a custom with the squid matrix. So we have the multiplexer 4-1, and the reason is we try to get like the minimize the areas, because one of the factor for the FPGA is the area and how much then you can put more logic on. So we did a custom multiplexer, because all the switch matrix and also the routing resources in the FPGA rely on the multiplexer. So we make a very core one, and then we use that, and we can successfully integrate it with the whole standard cell from Skywater, and implement the child. Yes.
I remember the first time I saw a decapped and micrographed FPGA, and I was amazed at how much area was spent just on the routing fabric.
That's right. Yes. So I can say yes, mostly up to maybe 80%. Yeah, 50 to 80% of the area used for the routing resources.
Yeah, it's incredible. Yeah. Okay, so another thing that I'm interested to come back to, which Dirk mentioned, was that you're using a custom extension and an instruction extension for the RISC-V processors. Can you talk a little bit about that?
I can do that, as Andrew told me quite intensely what we're doing. So it's essentially, we have on both sides of the fabric a RISC-V core, and from both sides, Andrew is driving in the operands A and B that normally go to your ALU, and he can, from different slots, multiplex results back into the register file, right? So logically, the fabric is placed in parallel to the ALU. Yeah, and that allows you to use a slot either by the left RISC-V, by the right RISC-V, or you may even use it to move data from one to the other, or compute on the fly, or daisy chain them.
It sounds so flexible and interesting. I mean, it probably will be horrible to write firmware for, but...
Well, there are some mechanisms that Andrew implemented for the instruction decoder that allows you to simplify it a little bit. Of course, at the moment he does it all in assembly, which means you have like quite limited complexity that you handle at the moment. But the instruction decoder has some means to synchronize the two cores, so that you say, okay, that the other works basically as a slave from the first one, which simplifies life a little bit. Yeah, and a few other means have been implemented. Yeah, for example, you have the problem that an FPGA fabric typically runs at much slower clock speed than, for example, the RISC-V. So we can add automatically wait states and those kinds of things. Or Andrew does that.
Thanks. So, Win, back to you. Could you talk to us a little bit about how you found the open source tools, OpenLANE? Did you run into any problems? What was it like getting your application together?
Well, yes, of course. We had a couple of problems, and at the moment, actually, I'm writing the report, and later we share with the eFPGA people, so to enhance some of the features. So I think for the first one, we're facing with the FPGA and for the tie. So we have so many I/O pins, and with the current feature from the OpenLANE, so it cannot handle well the how to distribute, how to grouping the pins together, because we want to do that hierarchy bottom up. So we stick the tie together, and so we need to align the pin together from the top to the bottom and on the left and right, something like that. And we need to group the pin together, and then we have to assign at exactly location, so where we want to put the pin to, right? So with the current OpenLANE flow, it doesn't support that. So, but I already mentioned that to eFPGA people, and they said they will implement in the next version. The other one is like the...
Can I just hold that thought? Let me ask a related question. So were you using Tritonroute to do the routing for you, or were you doing all the routing manually, programming?
No, program all them automatic routing.
Okay. Yeah. Okay, right. Okay.
Yes.
Thanks. And your second point?
So the second point is the density. So at first we try with hardening the tie with the OpenLANE flow, but I got the very like poor for the density for the tie. So I decided to at this point, so at this one, so we go with Cadence Innovus. So we can harden the tie, and then we provide as similar as the primitive cell or like the standard cell. So later on, if the user want to use or implement their embedded FPGA, so they can pick up the tie and stick them together. kind of like that.
I
didn't quite understand that that second point there. Could you repeat it?
Basically, so we harden the tie by Innovus to get the best
When you
optimization.
sorry, I think I just misheard it. Harden the tile, so that's the logic
Yes,
tile.
that's right.
Okay, and you used a different tool to harden that and get a little GDS block, and then you put that into OpenLANE and used OpenLANE to tile that.
That's right. Yes.
Okay, right.
So the reason is we want to get the as dense as possible, and then so with that hardened tie, so provide to the user later on. So the user just only pick it up and stick together, depend on the size they want.
Okay. Yeah, I was quite impressed when you said it was 6x10, because some of the other FPGA examples that I've seen have only kind of managed like 5x5 or something like that. And I think they were using OpenLANE to do everything. So maybe that you got some of that extra density by using the commercial tools to
That's
do
right.
that.
Yes. Actually, for the last one, for the first application, so we can go with like 10 by 12, and then we also include with the blockram. So the blockram, so normally it's called a lot of area for the silicon area, and with this we can get like 6 blockrams and also 10 by 12 COB or DSP blocks.
Yeah, it's pretty impressive. Out of interest, what are you doing for the block RAMs? Is that DFF RAM, or are you
We use in
using
the
bit cells?
open SRAM from the I think from Matthew.
Cool.
Yes.
Okay. And how was that to use OpenRAM?
Well, it's got a couple of problems with when integrating with the fabric, and I think it has a couple of like the internal DSC error, but that's reserved for memory. So we got a couple of like DSC report, but later on it's said we can waive all those DSC. And yes, for the DSC check, for example, so we can have to use the abstract view rather than the layout, so we can bypass all the errors.
I saw a lot of people struggling with OpenSRAM integration at the end due to DRC and things like that. I'm hoping that on MPW3 it's going to be a lot smoother.
Right. Yeah, I hope so. Yes.
There are also, if I can step in, a few optimization tools that we implement right now to get better density just using the OpenLANE flow, because our ultimate goal is really to have an open everything. To keep the barriers down, and also like what we did with the with the block RAMs, we are more than happy to embed the best IP that we find in the open source community. And what we really do is with Fabulous, it's like a framework, and we are standing on the shoulders of giants like Yosys and NextPNR and so forth. And this is really an enormous ecosystem where lots of people contribute super high quality IP. And we take this all on as much as possible. And the interesting thing is, it starts to work.
Yeah, so let's now transition to talking about, we're expecting to get the results back for MPW2 in December. So once you get your samples back, what's going to be the process for testing?
So Badia, as I said, it's part of his research project. He is generating all those test configurations, all sorts of configurations to characterize the chip. Yeah, so at the moment he's doing this for Xilinx ultrascale devices. But we want to do this all in a generic way that we can put in basically arbitrary architecture graphs and have then different ways to do the stimulus generation and the measurements. And that work is all running in parallel, so that if we get the chip on our desk, we can basically connect it directly to a UART to program or another interface and get hopefully some useful numbers out.
Excellent. One related question I had was the testing that you're doing or that you did for MPW2. Were you even doing things like simulating loading the bitstream into your custom FPGA?
Yes, because we also want, of course, to. That's actually an interesting one. So first of all, of course, if we tape out the chip, we want to know that the configuration mechanism works. Yeah, and that the whole addressing scheme and all these things work, and that we know exactly that we know if we write a configuration bit, how to get data to a specific position into the fabric, that this is all rock solid. But we use this also, Andrew is using this for emulation. So we basically we provide two pathways to test your system. And in Andrew's case, because it's relatively small with his RISC-V system, he can implement basically an FPGA emulated on top of an FPGA with the whole RISC-Vs on one large FPGA. And you can really configure that model with the original bitstream. It's fully binary compatible. And something that we have working in a beta version, but there is a little bit more work to be done, is that we essentially can take the FPGA fabric itself and we just hard annotate the configuration bitstream, and you can recompile again. And then you can emulate one specific circuit running on your fabulous FPGA on a relatively small FPGA. Yeah, so to give you a number, if you do the full emulation part, because we haven't done really much optimizations for that one, you need something like 80 times more lookup tables than the fabulous FPGA has. So that's the cost of that one. Yeah, but if you do it in this hard annotation of the bitstream and you recompile, then it's more like a 2 or 3 times more in area.
It's so meta.
If you want so.
Great. Okay. I think that is about the end of my questions. Is there anything else that either of you would like to add?
Almost as you said, as I said before, this is really an exciting time. We joined, if you want, so the whole open source arena relatively short time ago, but I'm really amazed how fast everything is moving. I'm really amazed about the enthusiasm of everybody contributing there, the ambition to deliver really high quality, the ambition to work together. And it's really fun doing all these things.
Great. Well, thanks so much, both of you, for your time. I'm really interested to see how things progress. Just as a last point, if people want to get involved with the fabulous FPGA framework or use it, who should they get in contact with?
Probably the easiest way is just through our fabulous Git repository.
Okay.
Yeah. So if you Google for fabulous FPGA, you will get our context, and yeah, we have actually a few external collaborators like Andrew. We have now one in Turkey, and there is a small community that starts to grow.
Great. Well, all the best with validating the results back from MPW2. I hope that all works really well. And very nice to meet you both, Dirk and Nguyen. Thanks very much for your time again. And I'll see you for the next interview when we find out how well the FPGA works.
Fingers crossed.
Okay, thank you.